Hello, I'm Seema and welcome to part 19 of the chapter Alcohols, Phenols and Ethers. We have been discussing the chemical properties or chemical reactions of alcohols and phenols. And we divided these into two categories where we said the first category is where the breaking of the bond takes place between oxygen and hydrogen. And the second category is where the bond breaks between carbon and oxygen. It could be from the aryl group, the carbon of the aryl group, or carbon of the alkyl group. That is the second category. But then we studied the first category, that is breaking of OH bond. And the first type of reaction that we studied in this was the acidic character of alcohols and phenols. The second type of reaction under this category is esterification, which I will be explaining in this video. We already know from previous knowledge of class 11 also that alcohols and phenols react with carboxylic acids to give rise to esters. And we know about the structural formula of an ester. The general formula of an ester is RCOOR-. That is R, let us say, C, the R is, this is R, C, double bond O, O, R dash. This is the structure of an ester. If you imagine, it could be just a derivative of a carboxylic acid. If this was RCOOH, this would be carboxylic acid. If the hydrogen is replaced by an alkyl group like R dash, it becomes an ester. So this is something that we already know. Both R and R dash are alkyl or aryl groups. Right? So when a compound has this kind of a structure, it would be a general formula, it would be an ester. So we study here that alcohols and phenols can react not only with carboxylic acids, but with acid anhydrides, with acyl chlorides, and they can release esters, or they can produce esters as a result of this. Alcohols and phenols react with carboxylic acids, acid chlorides and acid anhydrides to form esters. So let us look at these three. That is, if you have an aryl or an alkyl hydroxyl group with a hydroxyl group, that is, it could be an alcohol or a phenol. So since these reactions are shown both by phenols and alcohols, therefore in every reaction we have included we've written just one reaction for both. It could be an aryl group / alkyl group. If it is an alkyl group, it's an alcohol. If it's an aryl group, it is a phenol, right? So when an alcohol or phenol reacts with carboxylic acid, which is R dash COOH, if this is an alkyl group, R dash has been shown where R dash can be the same alkyl group as R, or it could be different. If it is different, it becomes important to specify that it is a different alkyl group. Therefore, we usually put the R dash. And even if they are the same, the R dash helps us to understand where did which group go. Which alkyl group is where, to follow what is actually happening with every group or atom. Where is it going? Where is it moving in a reaction? You know, here's a tip. Especially in organic chemistry, if you know which atom is moving where, it becomes very easy to memorize the chemical reactions. So, and that's the reason why we usually do the reaction mechanisms, because sometimes it becomes a little tricky where an atom or a molecule is moving. In those cases, of course, the reaction mechanism explains it very well, where, what went, and why is the final product the way it is. But here, I'll just be writing the structural formulae to make it a little clearer. So I've written each equation 2 times. Once is as it is given in your textbook, the NCERT textbook, and the second is where I've just written the structure a little more in details to be able to make it easier for you to learn it. So aryl ROH with R dash COOH. COOH is a carboxylic acid. This reaction takes place in the presence of an acid which is usually concentrated sulfuric acid. It's a strong acid and it is concentrated, which means this reaction has to be helped a lot. The condition has to be given and forced to react. But when it does react, what is formed as a result? An ester. So AR or R, as I told you, the bond that is breaking is between oxygen and hydrogen. So hydrogen here breaks, this bond breaks. This is the bond that is breaking. And in RCOOH, it is the OH that is breaking. The hydrogen from here and OH from here are resulting in the formation of HOH, that is water. And ArRO, the C joins here and forms ROCOR-. This is an ester plus water. Now, since we normally, how do we write esters? RCOOR-, isn't it? So when you look at this formula, it might confuse you a little that how is this an ester, because that's not how we normally speak it. So that's why I wrote every equation another time, just to explain how it is an ester so that you understand the bonding in the molecule. So ArROH, we do understand the bonding. This is the alkyl group or the aryl group, and this is oxygen and hydrogen. And the bond that is breaking, only hydrogen is going to move from here. While the carboxylic acid, the structure can be written as R-COOH. So the OH from here and the H from here are going to, this is going to break, this bond is breaking here and this bond is breaking here. Now do you see? The molecule, this one will flip, and the carbon, where it broke, breaking of a bond is nothing but oxygen had one electron, carbon had one electron, both of them take their own electrons and move away. Therefore, carbon is now left with one dangling electron, and here oxygen is left with one dangling electron. Both of them join together to form a bond. So, oxygen and this carbon, both of which were now had one electron each, which was not participating in bonding, they get together and form a bond, and therefore you have RO, and the carbon here joins, the double bond O, and R' remains as such. So this kind of flips to join that, and it actually doesn't flip. We are flipping it because we are writing the molecule like that on the board. In nature, when it actually happens, the molecules, they get attracted to the, and there are so many of them, and anywhere in the surrounding, wherever the orientation is right, the bonding will take place, and it will result in the formation of an ester. So this was the first category. Second, an aryl or an alkyl or alcohol or a phenol would react with, now what is this? R-CO whole twice O. It is an acid anhydride. Let us see how this molecule is formed. What actually is an acid anhydride? Anhydride means something from which a water molecule has been removed, dehydrated, anhydride, right? We take two carboxylic acids, RCOOH and RCOOH. Do you see this? If I remove a water molecule from two molecules of acid, that is H from one and OH from the other, right? Let us remove a water molecule. Now what are we left with? RCOO and RCO only, right? If we join these two with this oxygen, let us put this oxygen in the center and let both the carbons join this oxygen. Now what do we have? We have RCO twice and one oxygen. How do we write it? RCO whole twice O. That is how you would write an anhydride. But when you split the structure, this is what is happening. This is what the actual structure of an anhydride is, and this is how it is formed. An anhydride is formed from two carboxylic acid molecules from which one water molecule has been removed. It is like oleum, you know. In the case of sulfuric acid, if you remove water from two molecules of sulfuric acid, you get oleum, which is a far stronger acid than concentrated sulfuric acid. So this is how an anhydride acid, that is why it is called an acid anhydride, from which the molecule of water has been removed. So when acid anhydride acid anhydride R-CO whole twice. O is acid anhydride. When it reacts with an alcohol or a phenol, the same thing happens. Hydrogen will come from here. And what are you going to get from here to form an acid? What did you get? COR dash. So COR dash is what you will get from this molecule, the acid anhydride. It will join in the same way to form AR or R, OCOR dash, which is an ester, plus. Now what if COR dash is used? What are we left with? We are left with R dash COO. One R dash CO has been used. So what are you left with? R dash COO, and the hydrogen joins it to form R dash COOH. That is the carboxylic acid which formed the acid anhydride. That carboxylic acid is also produced. Again, look at the structures to understand it better. You had AR or ROH. Only the hydrogen was used from here. And from this molecule, it is R-CO, which will be used and which will join, or what leaves here is R-COO. Right? Hydrogen from here and R-COO, they combine to form R-COOH. Do you see? The oxygen here, if this bond breaks, then it has one electron, and the hydrogen has one electron, oxygen has one electron. Hydrogen joins this oxygen to form R-COOH, and this R-C double bond O, this carbon has one electron which joins the oxygen to form COOR-. Now, another thing I told you, when we look at this molecule, we think it does not look like an ester in our writing because the general formula that we have memorized is RCOOR. So from this you might get confused, but when you draw the structure, you see R-COOR. You're only moving in this direction. It is actually RCOOR only. Only it is written backwards. So here also you get R-COOR or R-COOAR. Whether it is phenol or alcohol, you get an ester and you get the carboxylic acid back. The third is where you can get it from acyl chlorides or acid chlorides. What is an acid chloride? Again, a carboxylic acid is RCOOH. When the OH is replaced by chlorine, it is known as an acyl chloride or an acid chloride. Okay? So you have acid chloride. Yeah. Acid chloride, the same reaction, AROH or ROH with R-COCl. Now this reaction, one more important point that was to be remembered here. In both of these reactions, if you see, they are reversible reactions. And we had to use strong concentrated sulfuric acid in all of these. From concentrated sulfuric acid, from concentrated H positive, from concentrated sulfuric acid. What happens, since these reactions are reversible, the products that are formed are not so stable. They would have a tendency to give you back the reactants. So what do? In these reactions, in the first step, what we do in this first reaction, we keep removing the water molecule. We keep removing the water that is formed immediately, so that if the water is removed, the reaction, the product is decreasing. And you have studied about it in chemical equilibrium, that when you remove the product, the concentration of the product decreases. Therefore, to match it, the concentration of the reactant, some of the reactant will form more product to regain the equilibrium. So that is how you will enhance the formation of the product, by immediately removing the water that is formed. Right? So then we come to this third category where we had pyridine. We were using pyridine base, and the pyridine is actually a base. Again, it is used to neutralize the HCl. The HCl which is formed is a strong acid. It will have a tendency to react with this and give you back the reactants, and you don't want that. So you add pyridine the pyridine is going to react with the HCl which will be produced as a result of this reaction, and since it reacts with the HCl, it will neutralize the HCl. The HCl will not be able to react with the ester formed to give you back the reactants. So the structure again, I wanted to make again, here it is an alkyl or an aryl group, OH, the hydrogen is removed from here, R-CO, the Cl from here, let me use a red pen. The Cl from this molecule and hydrogen from this molecule would result in the formation of HCl, which means this bond breaks and this bond breaks. Oxygen gets 1 electron, hydrogen gets 1 electron, carbon gets 1 electron, chlorine gets 1 electron. Hydrogen combines with chlorine, both the electrons here, to form HCl, and the oxygen combines with carbon to form R-COOAR, which is an ester. So reaction 1 and 2 are reversible reactions. Therefore, water is removed as soon as it is formed. In this case, the carboxylic acid will have to be removed. So as soon as water is formed in the first reaction, it has to be removed so that the reaction can be shifted to the right direction, that is towards the product. You can encourage the formation of the product. Similarly, in the third reaction, pyridine is added so that pyridine neutralizes HCl to shift the reaction in the forward direction, right direction or the forward direction. Now, another reaction that we call is acetylation. The acetyl group is nothing but the C double bond O group, right? In carboxylic acid also, like it is RCOOR, right? This is the acetyl group. So anywhere where the acetyl group is added is called acetylation. So acetylation is introduction of the acetyl group to alcohols and phenols. Acetylation of salicylic acid produces aspirin, and that is why we mention this acetylation. It is nothing but the same esterification reaction with acid anhydride, but the product that is formed is acetyl salicylic acid, which is also called aspirin. And since the acetyl group is being added, that is C double bond O is being added, it is also called acetylation. It is an esterification reaction, yet it is also an acetylation reaction. So let us see how aspirin is formed. You have salicylic acid. Salicylic acid is nothing but benzene ring, that is a phenol, with carboxylic acid group. It is a phenol in which the carboxylic acid is also present. So at the ortho position you have COOH and OH is there. This compound is called salicylic acid. It reacts with an acid anhydride, that is ethanoic anhydride, and in the presence of an acid, as we did it here, in the presence of acid, that is concentrated sulfuric acid, it will result in the formation of acetyl salicylic acid, which is called aspirin, and what will be formed? CH3COOH. I will again go to the same explanation which I have done for all three reactions. The O and H, this bond breaks here, and what is going to come here? COCH3. One of the COCH3s will be used up here, and the other one, that is CH3COO, will be left. The CH3COO which is left, if you remember, CH3CO, CH3CO are attached with an oxygen, right? So, and here oxygen and hydrogen, the bond breaks. So one of these bonds is breaking. If this is breaking, oxygen has 1 electron and the oxygen here has 1 electron. This oxygen adds the hydrogen and it results in the formation of CH3COOH, and this oxygen goes and combines with here and results in the formation of OCOCH3. Or rather, not oxygen, it is the carbon, because this O is actually CH3CO. It is the carbons which are attached to oxygen, not oxygen. When we write the structure like that, you can get confused on which atom is actually attached to which. So the structural formula always helps to understand what bond is breaking. So it is the carbon and oxygen. This bond breaks here and this remains intact. So what joins here would be CO, CH3. So the O was already there and COCH3 added to it. And if you write the detailed structure of this to see how is it an ester, I can do that also. This is COOH, and here you have O, COCH3. So CH3 COO phenyl group. It forms an ester, and since the CO is being added, it is known as acetylation. So acetylation of salicylic acid results in the formation of acetyl salicylic acid, which is also called aspirin. Right? So this was esterification. In the next video, we are now going to start with the second category of reactions, that is reactions which involve the cleavage of carbon-oxygen bond in alcohols. That is, these reactions, we had studied about electrophilic, nucleophilic, the different categories, how they are. I would encourage you to watch all the videos that we have done about the chemical reactions of alcohols and phenols till now, so that you are clear as we keep moving ahead with the next video. So if you wish to watch other videos of this chapter, please click the link that appears on top of the video. If you found this video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends. It gives me immense joy when my videos help children clarify their concepts. And when I get messages like I really scored very good marks, I got whatever percentage and I've got an admission in a medical college, I've admitted here and there, it gives me immense joy to know that I could be a part of the success of a child. So thank you for watching. Bye bye for now.